Year 13, Further Algebra, Lesson 2, Binomial Expansions where n is not a positive integer. So in our last lesson, we introduced the general binomial expansion which can be used for any value of n. Now, we did note at the end of the last lesson that if n is a positive integer, then this expansion is valid for any value of x. Now, additionally, if n is a positive integer, then this expansion will consist of a finite number of terms. Now, if n is anything other than a positive integer, so for instance, if n is a negative number or a fractional number, then this expansion is only valid if mod x is less than 1, i.e. if x lies between -1 and 1. Now, additionally, it's important to note that if n is negative or fractional, or possibly both, then the expansion will consist of an infinite number of terms. Now, if we're using the expansion in this format, then this part of the expansion here has got to be a value of 1. Now, if it's not 1, we need to adjust the expression so that we have a 1 here by careful use of factorisation, and we will look at some examples of this later on. Now, although the expansion in its general format is set up for a single positive x as the second part of the expansion, this doesn't matter. We can have anything here. We could have -3x plus 4x. We could have -4x squared as part of the initial binomial. And all we simply do is replace x in the expansion with whatever is the second part of the bracket. So for instance, if it was 1 minus 3x, all raised to a particular power, instead of x, we would replace x with -3x. But you will see that unfold in the examples that we are going to do. So let's take a look at the first example. We're going to find the first 4 terms in the expansion of 1 plus x to the power of -2. So we'll start really nice and easy here. And the first thing we need to do is identify our value of n. So clearly n is equal to -2 here. We're starting with 1 in the expansion, so that makes life nice and easy as well. And we simply have a plus x here, so we match the expansion formula directly. So here we go, 1 plus x to the power of -2, the first 4 terms. So again, I'm going to stack them vertically because that actually really does make life a little bit more clear. And then we'll collect the terms at the end. So my first term is 1. Now my next term is n times x. So n is -2, and x, of course, is simply x. So it's -2 multiplied by x. My next term is n multiplied by n minus 1 multiplied by x squared all over 2 factorial, and then my next term is n multiplied by n minus 1 multiplied by n minus 2 multiplied by x cubed all over 3 factorial. So hopefully you've been able to see that I've substituted in for n in each term here, and we go up to the term in x cubed if we want 4 terms of this expansion. Now we then need to simplify this, so 1 plus x to the -2 would be equal to, so let's look at the 4 terms that we have here. So our first term is 1, our next term is -2x. Now our next term, when we work this out, comes to a value of plus 3x squared, and then the next term after that comes to a value of minus 4x cubed. You can simply input this into your calculator to calculate each of the coefficients. Now, we could keep on going, because if you think about how the formula works, it's infinite. We can carry on creating more and more terms each time. I've only been asked to calculate the first 4 terms in this expansion, so I'm going to stop here, and I'll put a plus ... to indicate that there could be more terms in this expansion. before we finalise our answer, we need to state the set of values for which this expansion is valid. How do we find that out? We look inside this bracket here, and this expansion is valid for mod x less than 1, i.e. for values of x which lie between -1 and 1. Now, this might seem unclear to begin with, but we will explore this properly in more detail later on. Now, one word of warning, I do sometimes see people when they're asked to expand something like 1 plus x to the -2, I sometimes see people do this, rewrite it as 1 over 1 plus x squared, which is not exactly wrong, it's a valid algebraic step, and then write it as 1 over 1 plus 2x plus x squared. So they simply express it like this as an algebraic fraction. Now, algebraically, this is perfectly correct, but it's not a binomial expansion. And if you are asked to conduct a binomial expansion of something like 1 plus x to the -2, you've got to use this result up here and complete a term-by-term expansion. You can't just do what I've done here in green in this example. So, second example, we're going to find the first 5 terms in the binomial expansion of 1 minus x to the -3. So first job, we need to identify what the value of n is. So n clearly equals -3 here, which means everywhere there's an n in this formula, in this binomial expansion, we're going to replace it with n equals -3. The next key thing is to look at the format of the expansion. Now, the first part of this is absolutely as it should be. We have the 1 that we need. Now, the second part of the expansion is interesting because it features a negative x. Now, that means everywhere there is an x here, we need to replace x with negative x and then perform the function. So let's work through the expansion. So my first term is going to be 1. My second term is going to be n multiplied by x. So my n is, of course, -3, but my x is negative x. Now, my third term, so I'm up to this part of the formula, is n multiplied by n minus 1 multiplied by x squared all over 2 factorial. So that is -3 multiplied by, and I'll just write -4 here for simplicity, multiplied by x squared, which is -x all squared, and the whole thing is written over 2 factorial. Let's keep going. Term 4. So we're up to this part of the expansion, substituting in for n. So that's n minus 1, which is -4, n minus 2, which is -5, multiplied by x cubed, which of course is -x all cubed, and then the whole thing is over 3 factorial. And then our last term of the 5 that we need to work out, well, we don't have the formula written down here, but of course the pattern is going to continue. So it will be n minus 1, n minus 2, n minus 3, x to the power 4 over 4 factorial. So you need to be able to continue the pattern of the expansion, even if in the formula booklet, for example, you can only see the first 4 terms written down. So let's substitute in. So that's -3, -4, -5, and then we're up to n take away 3, which is -6, all multiplied by x to the power 4, which is -x to the power 4, and then the whole thing divided by 4 factorial. And then, of course, we have to simplify each of these terms, being very careful because, of course, the -x raised to a power will result in some positive and some negative terms. Use your calculator, see if you can simplify each of the terms and find out the final expansion. So 1 minus x to the -3 equals, now we know the first term is 1, got that done. The second term is going to be -3 multiplied by -x, which is positive 3x. See if you can work out what this term is going to be and whether it's going to be positive or negative. Hopefully you got it. It is positive and it is positive 6x squared. So let's check whether you got the right answers for the last two terms here. So term 4, we have positive 10x to the power 3, and for term 5 we have again positive 15x to the power 4 plus ... because again this is in truth an infinite series. Now what about validity? Again, look inside the expansion here and that will give us our validity condition. This is valid for mod x less than 1, or alternatively x between -1 and 1. This will change in subsequent examples, as you will see. So, example 3, we're going to find the first 4 terms in the expansion of 1 plus 4x to the power of -1. So first job, as always, is to identify our value of n, which is equal to -1. Now, let's look at the terms in the expansion. We begin with a 1 as required, so that's absolutely fine. Now, the second part of this, however, contains a 4x. Now, that means everywhere there is an x in this expansion, we've got to replace it very carefully with 4x. So let's start working through our expansion. So my first term is simply going to be 1. My second term, which is n multiplied by x, so I'm up to here in my expansion. So that is going to be n, which is -1, multiplied by x. But x, remember, is being replaced by 4x. So wherever there's an x, we need to replace it with 4x. What about my next term? Let's start building these up. Term 3. So we want n minus 1, which is -2, multiplied by x squared. So that's 4x all squared, all over 2 factorial. So just to be very clear, I've completed this term here. So my fourth term is going to be n minus 1, n minus 2, all multiplied by 4x to the power 3, all over 3 factorial. And then we're going to simplify each of these terms and then combine them to create our 4-term expansion. Please be careful as you do your expansion. Remember, something like 4x all squared is equal to 16x squared, not 4x squared. Be very careful as you expand each term. So let's simplify. So this becomes -4x. This term here becomes positive 16x squared. This term here becomes -64x cubed. So my expansion of 1 plus 4x to the power of -1, or the first 4 terms of this, are 1 minus 4x plus 16x squared minus 64x cubed ... Now, validity. This is going to be slightly different because of the contents of this bracket, because it's no longer a single x. So this time, rather than mod x is less than 1, which is what we would say if the expansion looked like the generic example, we have mod of 4x less than 1. Now, divide both sides of this by 4, which we can do. 4 is positive, so it's absolutely fine. This gives us mod x is less than 1/4. Now, what does that mean? That means x lies between 1/4 and -1/4. So this expansion is only valid for values of x that lie between -1/4 and 1/4. And again, later on, once we've had a look at a number of examples, we will see exactly what this means. So, a slightly different example again. Find the first 4 terms in the expansion of the square root of 1 minus 2x. So our first job is, of course, to identify the value of n. And you can't do that unless you rewrite this as 1 minus 2x to the power of a half. So we now have a non-integer value of n equals 1/2. Now, is the expansion set up in the way we need? Yes, it is, because the first part of the expansion starts with a 1, so we're absolutely fine there. Now, the second part of the expansion, however, is negative 2x, which means wherever there's an x in the right-hand side of the expansion, we need to replace x with negative 2x. So let's see if we can work this out. So we're expanding 1 minus 2x to the power of a half. So my first term is still going to be 1. My second term, remember, is nx. So n, of course, is a half. X is being replaced by negative 2x. So I've completed this term here, nx. We're now going to take a look at this term here, which is a little bit more complex. So that's my term 3. So this is n multiplied by n minus 1, which I'm going to write as a half minus 1 for the moment, and then I'll just input that into my calculator. This is multiplied by negative 2x to the power of 2, and it's all divided by 2 factorial. And then we have term 4, which is n minus 1, n minus 2, multiplied by x, or negative 2x, which is our x replacement here, all to the power of 3, and then the whole thing is divided by 3 factorial. So just to clarify, I finished this term here as well. Now, let's have a go at simplifying each of these. You can input the calculation straight into your calculator. Please remember, as we've warned previously, to be careful about, for instance, negative 2x all cubed in that last term. That would give you negative 8x to the power 3 when you expand that part. So be very, very careful. You may wish to work out the terms yourself and then check if you've got the correct answers. So did you get the correct answers? So these are the first 4 terms in yellow, and we can put these together. So our expansion, 1 minus 2x to the power of a half, will look like this. 1 minus x minus a half x squared minus a half x cubed, and then I'll just put plus ... at the end. I don't have to put minus ... at the end. And what about validity? Well, again, look inside the expansion here. It is going to be valid for mod 2x less than 1, which simplifies to give me mod x is less than a half, or if you prefer, x lies between minus a half and a half. Again, more on that later on. So as we build up our repertoire of examples, let's look at the next one. We have got to find the first 4 terms in the expansion of 1 over the square root of 1 plus 6x. So immediately you should be thinking about how to rewrite this in a more familiar format involving an index. So this would of course be 1 plus 6x to the power of negative a half. So we can see n equals negative a half. Let's investigate this expansion. It begins with 1, so that's absolutely as we want it to be. The second part of this is plus 6x rather than simply plus x. So of course this means we need to replace x in the expansion with 6x, but it's a positive 6, so that makes our work a little bit easier. So let's start listing our terms. So term 1, here it is, it's just 1. Term 2 is of course equal to nx, so that's negative a half multiplied by x, but of course x is being replaced by 6x here. Let's keep going. Term 3, let's build it up. n minus 1, then multiplied by x squared, which of course is 6x all squared, all divided by 2 factorial. So just for reassurance, we've just substituted into this part of the expansion. Now, term 4. Let's work that out. So that's n minus 1, n minus 2, x cubed, all over 3 factorial. So again, what have I done? I've substituted into this part of the expansion. Now, I would recommend taking your calculator and working out what each of these terms simplifies to very, very carefully. Remember to raise 6 to the necessary power as you evaluate each of the yellow sets of brackets. Be careful with the negatives as well. So let's see if you worked these out correctly. We'll do them in a different colour for clarity. So term 1 is just 1. Term 2 works out to be negative 3x. Our next term, 27 over 2x squared, and our last term, negative 135 over 2x cubed. Now, let's write out our expansion so we can see it clearly. And it's equal to 1 minus 3x plus 27 over 2x squared minus 135 over 2x cubed, dot, dot, dot. Now, validity. Let's take a look very carefully inside the brackets here. My expansion is going to be valid for mod 6x, so the second part, less than 1, divide both sides by 6, so that's mod x less than 1/6. And again, if you want to write it out without the modulus sign, the expansion is valid for x between minus 1/6 and 1/6.
So we're just going to segue slightly into talking about the use of your graphical calculator. Now I know this is a slightly older model than the FXCG50 which most of you are using, but the key presses will essentially be virtually identical. Have a look at the calculation that I've inputted, which relates to the previous example that you were working on. Now, it's quite clunky if each time you have to do a step, you have to input negative 1/2. Even if you convert it to negative 0.5, there's a danger that you might make an error here. So, what might be an easier way of doing this? Well, store a number in a memory. So I'm going to store the value of negative 1/2 in a memory. How am I going to do that? Well, I've inputted negative 1/2, and then I'm going to press this arrow here, hopefully you can see that, and I'm going to store it in a memory. Now I can store it in any memory that I want to, but well, we're using n in the question, so I'm going to store it in memory n. So to do that, I press alpha, the red key there, and then I press n, execute, and it's stored in memory n. Now every time I want to use my value of n, I press alpha, I press n, and there it is. So if I want to input the calculation, which was n multiplied by n minus 1, close bracket, multiplied by n minus 2, which I had up on the screen a minute ago, minus 2, and then now that was multiplied by 6x all cubed. I obviously can't input x, but I can input 6 to the power of 3. I get that, and then of course we were dividing by 3 factorial, so that's divide by 3, and then to access the factorial, remember we went through this in the previous lesson, you can see all the key presses there, and then I get negative 67.5. If I press the FD button, there is my negative 135 over 2, and it's much neater and much easier, and you're much less likely to make a mistake if you keep inputting n or some other letter than if you have to input negative 1/2 or some other complex decimal each time. So make sure you practice doing this. Another good way of storing a number is, for instance, let's say we had to input 0.125, arrow, just press this X button here. And then every time you want to do a calculation, let's see, x cubed plus, plus 2x squared, it's much easier to do that with the value stored as x than having to retype 0.125 each time.
So let's move on to example 6. As you can see, we've steadily built up to more and more complex examples. So we are going to find the first 4 terms in the expansion of 1 minus 3x squared all to the power of negative 2. So n first of all equals negative 2. The expansion begins with 1, as have all the examples we've done so far, but instead of a single x we have, and again more complex here, negative 3x squared. So remember, every time you see an x in the binomial expansion formula, you need to replace it with negative 3x squared. Okay, so let's start off our expansion. Term 1 is simply going to be 1. What about term 2? Well, that's going to be n multiplied by x. So what is our n? It is negative 2. And x, of course, is being replaced by negative 3x squared. Term 3. We want n minus 1, which is negative 3, multiplied by our value of x, all squared, like that, and all divided by 2 factorial. What about term 4? We want n minus 1, n minus 2, multiplied by x, all cubed, and then all over 3 factorial. And we're going to evaluate each of these terms very carefully. Remember, if you're evaluating something like negative 3x squared all cubed, be very careful. What happens when you cube negative 3? You get a value of negative 27, and then when you cube x squared, you get a power of x to the 6. So that's going to be quite interesting in terms of the individual terms that we end up getting and each of the powers of x. So let's have a look. I'm going to simplify each of the terms, write out the expansion, see if you agree. So my final answer is 1 plus 6x squared plus 27x to the power 4 plus 108x to the power of 6 plus ... Now, validity conditions are a little bit more interesting in this particular example. So I'm going to move on to the next slide to allow us a little bit more space to explore this. So in the previous example, we've just expanded 1 minus 3x squared all raised to the power of negative 2. So what about the validity condition here on x? So let's look inside the bracket here again. This is going to be valid for mod 3x squared less than 1. Now, let's simplify this. Divide by 3. That gives us mod x squared is less than 1/3. At this point here, we can lose the modulus symbol because x squared cannot be negative. So we can simply write x squared must be less than 1/3. So x squared is less than 1/3, and we need to find the values of x which satisfy this result. Now, this is a quadratic inequality. So when we're solving quadratic inequalities, if you recall, we need to be very careful and we need to sketch a graph. So here's my set of axes. And here is my sketch of y equals x squared. Now, where does y equal x squared equal 1/3? So let's imagine we have a line drawn, none of this is to scale, which represents y equals 1/3. Now, at the points of intersection, we know this is where x squared equals 1/3. So where does x squared equal 1/3? Well, it equals 1/3 when x is equal to the square root of 1/3 and negative root 1/3. But we are trying to solve x squared is less than 1/3. So where would we find that? Well, we would find that in this region here, because that is where the x squared graph falls below the line y equals 1/3. Now, which set of x values generates this region? Well, very clearly, it's these x values lying between negative 1 over root 3 and positive 1 over root 3. So our solution set is that x must be between, and we'll write it out as 1 over root 3 and negative 1 over root 3, like that. You can rationalise the denominator as well if you want to. If you want to write it out as a modulus, this tells us that the modulus of x must be smaller than 1 over root 3. So these are the validity conditions for our expansion. So we're now going to spend a little bit of time thinking about these validity conditions that we have discussed. So let's choose as an example to reflect on the expansion we did earlier, which was 1 plus x to the power of negative 2. It's a very simple result. We got 1 minus 2x plus 3x squared minus 4x cubed plus 5x to the power 4, etc. It's a very easy expansion to generate terms for. Now, what were the validity conditions of this expansion here? Now, this was an easy one looking at the contents of the brackets here. This is simply valid for mod x less than 1, or written out this way, x is a value between negative 1 and 1. Now, let's see what this actually means. So I'm going to choose a value of x. So let's say x is equal to 0.2. Now, that satisfies the validity condition. You can see 0.2 lies between negative 1 and 1. Now, if x is equal to 0.2, what is the left-hand side of the expansion equal to? And by the left-hand side of the expansion, I mean this part here. If we input 0.2 into that, what do we get? Well, you can check that on your calculator and you'll find you get a value of 0.694 recurring if you replace x with 0.2 in the left-hand side. So if you're just calculating 1 plus x to the negative 2 directly. Now, what happens if you input x equals 0.2 into the right-hand side of the expansion? Now, what do I mean by the right-hand side of the expansion? Well, I mean all of these terms here. Now, obviously, I can't input into every single term in the expansion because there are infinitely many terms in the expansion. But I have 5 terms here, so what I'm going to do is just input into these terms here. So I'm going to replace x with 0.2 in 1 minus 2x plus 3x squared minus 4x cubed plus 5x to the power 4. This will be a good opportunity for you to practice storing x equals 0.2 as x on your graphical calculator and then typing the expression out in terms of x, rather than inputting 0.2 every single time. Now, what do we get as an answer? Well, we get 0.696. Now, look at these. That's not a bad match, so that we can see, of course, the right-hand side is an approximation for the left-hand side. 1 plus x to the power of negative 2 is a single algebraic statement, but the expansion on the right-hand side is a series of terms which approximate to 1 plus x to the negative 2. The more terms you include, the better the approximation you have for your original statement, your original algebraic expression. We've got 5 terms, and with just 5 terms, you can see when x equals 0.2, the expansion gives us a good approximation to the original function. So that's what happens when we choose a value of x that lies within the valid range of x values. What would happen if we chose a value of x for which the expansion is not valid? So I'm going to choose x equals 5, and I'm going to input this into the left-hand side and the right-hand side of the expansion, and we're going to compare and contrast. So let's input into the left-hand side. So again, that means I'm substituting just into 1 plus x to the power of negative 2, and you can see that gives you a value of 0.027 recurring. What happens if you substitute x equals 5 into the right-hand side of the expansion, so the 5 terms that we are including in our expansion? Well, you'll find very quickly that you get an answer of 66. Now, have a look at this. The actual value of the function, 1 plus x to the negative 2 at x equals 5, is 0.027 recurring. the approximation, which is the expansion, gives us a value of 66. That's such a poor approximation for the actual value, which is tiny in comparison. So this is why when you are conducting a binomial expansion and your value of n is not a positive integer, i.e. it is a negative or fractional number, then it's really crucial that you set out your validity condition for your expansion, because your expansion will not will not hold for certain values of x. We're now going to have a look at this graphically. So we're going to explore validity conditions in a little bit more detail, and also the expansion itself and what it actually means. We'll take this from a graphical perspective. So here is the graph of y equals 1 plus x to the power of negative 2. Now, if you recall, the expansion that we wrote down for y equals 1 plus x to the power of negative 2 was equal to 1 minus 2x plus 3x squared minus 4x cubed plus 5x to the power of 4, etc. And what we're going to do is we're going to take sections of that, plot the graph of the sections, adding an extra term each time, and see how closely this resembles the graph of the actual function 1 plus x to the negative 2. So have a look at the graph here. What we've done is essentially take this expansion, but we've excluded all of these terms here, and we've just taken the first term, and we've plotted that as a function, y equals 1. Now, as approximations go to the graph of 1 plus x to the power of negative 2, this is a very poor approximation. Obviously, that's because we've only included one term. Now, this time, we're going to cut the expansion off after two terms, and we're going to plot the graph of those two terms. So the straight line here is the graph of y equals 1 minus 2x. Now, it's a slightly better approximation than y equals 1, but it's still far from perfect. Y equals 1 plus x to the power of negative 2 is a curved graph, and y equals 1 take away 2x is a straight line. So we don't have a good approximation with just two terms. Now, things start to become a little bit more interesting when we cut off the expansion after three terms and we plot this. So this is a graph of y equals 1 take away 2x plus 3x squared. So we're taking the first three terms of the expansion. Now you can see in this region here that the orange curve, which is the part of the expansion, matches quite closely to the original function of y equals 1 plus x all to the power of negative 2. In other parts, we don't have as good a fit, but we're actually getting quite a good fit in at least one part of the x domain. So we keep going. This time, you can see the blue curve here is comprised of the first four terms of the expansion. So it's 1 take away 2x plus 3x squared minus 4x cubed. Now you can see that we get a really good fit across here between the blue curve and the red curve. So the more terms that you include in your expansion, the closer the curve of these terms, comprised of these terms, will match against the curve of your original function, the one that actually is being expanded. So let's see what happens as we continue to include more terms. So hopefully you can see over here, the green curve is the graph of y equals 1 minus 2x plus 3x squared minus 4x cubed plus 5x to the power 4. So we're including 5 terms in our expansion. And you can see that you get a very good fit. Again, only for some x values, but for those x values, the match is very, very, very close. So in this highlighted region here. So now I've jumped to include 14 terms. You can't quite see all of them here. I'm not going to write out the whole thing, but I've gone up to x to the power of 13. Now, have a look at the graph. We get a very, very good fit between here and here. So the green graph is almost superimposed on top of the graph of the original function. Have a look at the x-axis. Can you see that this point here is x equals 1? This point here is x equals negative 1. So between x equals 1 and negative 1, the approximation, i.e. the expansion, matches the original curve very, very closely. If you go beyond x equals 1, well, here's the original function, and here's the expansion. And again, if you go below x equals negative 1, the green curve clearly doesn't match the red curve at all. And that is another explanation which justifies why you have to give a validity condition. So the expansion of 1 plus x all to the power of negative 2, which we've now seen is 1 minus 2x plus 3x squared minus 4x cubed, etc., is only valid when mod x is less than 1, i.e. when x lies between 1 and negative 1. As you can see, looking at the yellow arrow on the diagram, that is where the expansion, which is the green curve, matches the original function y equals 1 plus x all to the power of negative 2, which is the red curve, very closely. When you move outside of that region, you do not get a nice close fit between the two.